So, let's tackle a problem or something. Sketch the figures and find the arc length and the area of each of the following. All right, so the sketches are variable. It depends on the nature of the file, but you don't need me to tell you that. So I don't even have to be talking about polar graphs to think like that, you know? Like if it's an easy equation, it's gonna be an easy graph. If it's not an easy equation, it's gonna be a rough graph. All right, so that's the same idea here. All right, but r equals 3, we learned 2 classes ago, maybe 3, that this is the equation of a circle with center at 0, 0, and radius equal to 3. All right, which is good news and bad news. It's good news because that means that you know that you could find the answer without calculus. It's bad news because we have to find the answer with calculus. All right, so it sucks. It's like I already know the answer, but actually no, I'm overselling that. It's a good problem to start with because when when you have a problem like this and you already know what the answer is going to be, I mean I can throw this one on the test too. You know what the answer is supposed to be. Once you get that answer, you're pretty confident and you can move on to the next one with not a care in the world. All right, so we're gonna start with the well. It said, oh, you know what? That's a legacy typo. That typo's been there for like a solid decade. It's not a significant one. It's just one that bothers me. Find the arc length and area. Switcherooski. Because I introduce area first and then arc length on the previous page. So for consistency, even though it says find them both, I gotta do them both. I want the directions to lead the reader to think area first, then arc length. All right, so that's a typo for somebody if you want to claim it. I'm pretty sure I pointed that one out before. It's just nobody's ever claimed it. They're probably thinking somebody else is going to get it. All right. So, well, we could do the diagram pretty easily. Don't need a calculator for that. I'm going to pretend that's a circle. Its radius is equal to 3. All right. Using a step of 0.01. All right. When you're sketching a figure and I give you a theta step, and that theta step is really small, all I'm telling you is that it should be a smooth curve. All right. So smooth curve. All right, if the theta step were large, then you'd be looking for something more angular. All right, so we got that part. Now, what we're gonna do is apply our rule. All right, we know a circle, like any circle, is gonna go around 360 degrees or 2 pi radians. So it's gonna start at 0, it's gonna end at 2 pi. So my domain is consistent in that it represents the beginning and the end of the graph. I don't have to worry about this being one of those kind of graphs that's going to wrap around itself a couple of times based on the domain. Now, if this said r equals 3 on 0 to 4 pi, I would be concerned because I'd be like, wait a minute, a circle begins and ends in 2 pi radians. So if it's 4 pi, it may go around a couple of times. For area, that it wouldn't matter. You know, like it's one of those things where once you figure out where the circle begins and ends, that is the area that will be captured. You can go around it 20 times, it's still going to be the same area. But for arc length, it does matter because I'll tell you right now, if I'm running around a track and you tell me I got to run around it 30 times, I don't care how much area is contained within the track, I got to run around the edge of that thing 30 times, that's going to be a problem. All right, so arc length, it matters in terms of the length. So in that regard, you just go with it as is. The area, you have to be very careful about where the graph begins and where it ends. All right, so this one's a simple case. In other cases, I'll walk you through it. You would need to either use the calculator to support or solve for where the graph hits the polar axis. All right, and I'll show you how to handle that also. All right, so bottom line is I could jump right into the 1/2 r squared d theta. So area is equal to 1/2 on the interval. All right, we're starting at 0, going to 2 pi. 1/2. I'm going to write it in general terms first. R squared d theta. Now you could integrate this as is. As it turns out, that theta is the integration variable, which means that that r could be treated as constant, which is actually the foundation of multiple integration. But that's a different story for a different day. What we're going to do is, since we know that r is a constant, r is 3, and it's always 3 in this world, I could just chuck that right in. And we'll be looking at the antiderivative over the interval of 0 to 2 pi. This is going to be 9/2 d theta. All right. Integrate, we're looking at 9/2 theta over 0 to 2 pi. Plugging in the 2 pi gives you a 9 pi. Plugging in the 0 zaps away, so we're looking at 9. Why is this glitching on me? Come on, write something, for crying out loud. Now it's writing stuff that I don't want it to write. So it's going to be 9 pi. All right. This is one of those cases where, yeah, you can put it in the calculator, but, I mean, it's a constant that you're integrating. You just slap the variable on it and call it a day. You know, so this is not something that you should shy away from doing by hand. Right? So that's the area, 9 pi. Well, area is pi r squared, right? Radius is 3. Pi times 3 squared would be 9 pi, so we're comfortable with this as a final answer. All right. So then what we need is the arc length. So we know that the circumference is something that we can figure out pretty easily also. All right. So going into the problem, we know what we're up against. So arc length, S for some reason, over the interval of 0 to 2 pi still, the square root just debating. But you know what, let me is that time. All right, that I've come to a decision. All right, so anyway, r squared, so 3 squared and then it's the sum of the squares, so plus I need dr d theta squared. Well, r is equal to 0, r is equal to 3, Stolen Thunder. Yeah, so r is equal to 3, so if I want dr d theta, derivative of a constant is equal to 0, so 0 squared. Because it's really the sum of the square part of it that I want to get across, the Pythagorean relationship. It's actually pretty cool, so it's worth looking into. But I think we'll do that. We'll do that beginning in next class. Okay, so 0 to 2 pi, looking at 3 d theta, integrate, looking at 3 theta over the interval of 0 to 2 pi. And then when you plug and chug away, you get 6 pi minus 0, so 6 pi is it. Oh, my pen turned off, that's why. It's not glitching, it's just off. A little bit. Yeah, I'll actually charge it today. So
Are those charging really fast? In a minute? Like full battery? Or something like that?
yeah, it goes pretty quickly, but I think I'm also like, I struggle because I'm a little colorblind. I know when this starts turning purple, that's when it goes purple then red.
What's that blue right now?
It's solid blue, right?
Yeah, it's solid blue.
Is there a hint of purple in there?
Maybe.
Not that, okay, so. Yeah, that's the whole issue. And also there's the other thing.
Why do you have to turn it on?
Oh, because it's, what is it, they call it an adaptive pen? So this interface won't work unless it's powered. This one will. So this is just a regular stylus, this part of it. But this part is like, it's not an Apple Pencil, it's not Bluetooth, but it's, yeah. So it'll actually, you know, the weight of the writing will vary depending on the pressure put on it, but only if it has the power behind it. Oh wow, the Mets won. They pulled it out in the ninth. Look at that. I mean, the season's over, so it doesn't matter, but like, that was nice. Because before class started, I took a look and it wasn't looking good. Oh, Alonso, 49th homer, rookie of the year. Just another instance where a Met's gonna have an individual accolade for the team stuff. Yeah, so circumference of a circle is 2 pi r. Double the radius, you get 6. Multiply by pi, you get 6 pi. So we're in pretty good shape there. So we're verifying really that this is not the demonstration of intense Calc 3 knowledge and polar coordinate stuff. However, I think you'd like it to be, because if I put many problems like this one on the test, you'd be thrilled, because there isn't really much to do, right? And even the integral part of it isn't that bad. The one thing that, one of many times I'll say this, that you need to be mindful of this, is that the integration stuff is not the thing that should be intimidating you in this course, all right? You've already been assessed on that. I'm not looking to assess you on that again. So anytime we come across an integral, if it's a definite integral, pop it in the calculator and move on, all right? It's different in other people's classes. I don't care about other people's classes. This is my class. In my class, you're allowed to use a calculator to get the solution to definite integrals. There will be plenty of instances where you have to do indefinite integrals by hand. You'll earn your keep on that. So when you see a definite integral, so you're given bounds, chuck it right in the calculator and don't even give it a second thought. Because if you spend time trying to do that kind of thing out by hand, it's time that is not well spent, all right? You're gonna run out of time for something that does require you to work it out by hand. All of that is me gearing us up for number 2, because this is not a circle equation, it's a limacon, all right? And in that limacon, we got our work cut out for us, all right? We have to create the sketch of the graph first. All right, so as easy as number 1 is, that's how difficult number 2 is in comparison. All right, so just kind of getting you oriented. All right, so first thing we want is a sketch, and the reality is you want the sketch. You do not want to shy away from the sketch. You don't need to do it by hand though. All right, a sketch is a sketch. The only time that you need to actually have it by points is when I say create the graph, and I'll say things like be sure to include the scale and label this, that, the other thing. But if I say create a sketch, a rough sketch is fine, but it still has to be there. All right, so let me get the calculator out. So we're looking at clear 2 plus 4 times the cosine of theta. I'm just going to graph it. This is our Lima sum. Structure is all we care about. I want an idea of what this thing looks like. All right, so, and again, sketch. Yeah, I'll give you your sketch right here. I'll show you your sketch right here. Look at that. Perfect sketch. Full credit. All right. The characteristics are what's important. I'm done with this. We're gonna do everything else. At least until we get to the part where we have to integrate stuff, we're gonna do everything else by hand. All right. So I need to know where this graph begins and where it ends. Sometimes watching the graph actually be generated on your calculator, sometimes that gives you a sense in and of itself. But we could also solve for it. We know this graph is going to go through the pole. All right. So if you actually watch it get graphed, you'll see it'll start here. It'll go through the pole. It'll wrap around, and then it'll finish up here. All right. So what I'm going to do is a couple of things. I'm going to find where this equation is equal to 0. So that's a classic calculus technique. Honestly, if you think back to Calc 1, Calc 2, if you were ever in doubt, I have no idea what to do with this problem, take an equation, set it equal to 0. It's probably the right thing to do at some point, right? So that's what we're doing here. All right, so 0 equals 2 plus 4 cosine theta. I'm going to subtract the 2. So negative 2 equals 4 cosine theta, which means cosine of theta, if I divide the 4, it's going to be equal to negative 1/2. A unit circle thing, it's just there all the time. It's crazy. It's like I wasn't lying before when I said the unit circle is important. All right, so going around your unit circle, now we're forced into the world of radians here. In some cases you have a choice, in this case you don't, because the domain given to us is in radian form. So we're stuck with that. All right, so going around the circle, we know that in the second quadrant and in the third quadrant, cosine is negative. That happens at 2 pi over 3 and 4 pi over 3. All right. So that tells me the angular measures for which the graph, and I'll highlight it here. I'll just do a little, oh, no, that's not what I wanted to do. Scroll up a little bit. Undo. Scroll up a little bit. I'll underline this, and then I'll highlight the point on the graph. That tells me where it's going to cross the pole. All right. I would also need to know where it's going to cross that polar axis. All right, so you could start thinking in terms of that, but I think that's pretty straightforward, because if you're just looking at the picture, well, if it's on the polar axis in terms of theta, that's going to happen at 0 radians. All right, because it starts at 0 and ends at 2 pi. All right, so here's my 0 radians. 0 radians, not ORAD. But then it works its way around in this direction, then this way, then this way, and then finally this way. So then it finishes up at 2 pi. So you're getting a sense of the characteristics of the graph. But like I said, sometimes just looking at the picture gets the job done too on the calculator. So let me bring that back up and show you how you could kind of wiggle your way through that information without going too crazy with the algebra and the trig. So in your window, the first thing that I would recommend is verify that you're only going to get one complete loop in the given domain. All right. So it might be weird to think like how can I verify that? Well, the default is 0 to 2 pi. I can clear this out and type in 2 pi and be really sure that that's the case. Yeah. Okay. There's the whole graph. Now, instead of 2 pi, what I'll do, so I'll hit enter, it converts it to decimal. I'll just dial it back a smidge. All right, instead of 6.28318, blah, 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 I'm gonna put in 6.2. All right, because if I dial back my theta max a smidge, just short of the full domain, then I should have just short of a full graph. So hit graph, I have just short of a full graph. All right, so it looks like I'm not at the point where I would be worried about overshooting it. But let's say, for example, and I'll show you where this really becomes an issue. The problem says 0 to 3 pi in the domain that's given. It's the same graph as 0 to 2 pi, right? I will have overshot the endpoint by a lot. All right, so it would have started here, it would have went around, it would have completed the loop, and then it would have started the loop again. All right, but it's overwriting the graph that's already there. So then I would say, okay, well, is that too far? So let me try 2.5 pi. It's still too far. All right, so then I'll try 2 pi. Is it too far or is it just right? I don't know. So I'll try something a little bit less than 2 pi. And that's where I settle in on, clear 6.2. 6.2 is just a smidge less. So a smidge less than the full domain should give you a smidge less than the full graph. All right, so that's a way of verifying that what you're dealing with is the entire graph over the given domain. And you can do the same thing with the circle. You know, if you had r equals 3, you plug that in. Instead of having it go from 0 to 2 pi, have it go from 0 to just a smidge less than 2 pi. What's that?
I don't think it's such in the middle. I think it's 10.
Doesn't? They screw it up?
Put in 1.
The plug-in is 0. Oh, it should be 6. Yeah, sorry. I identified the wrong spot. Yeah.
I just put in 1 there, just like where it started.
Yeah. So that's the other thing. Okay, so let me just fix that. Which is weird because I had it labeled correctly initially, and then I just deviated from that for some reason.
That can be right.
Yeah. So, yeah, that's the beginning. And then everything else I think is, let me get rid of the 2 pi. Now you could actually watch it graph on your calculator, so that's kind of a nice thing. It's actually a pretty significant flaw in the programming of the calculator, but it's a flaw that you could benefit from, so it's good. But for me, it just appears, right? So if I want to get a sense of how this graph looks, I could just start working my way around. 0, instead of going from 0 to 2 pi, I can go from 0 to like 1, like you said. Graph, that gives me a little bit of it. Then maybe 2. Then maybe 3. Or I'll just go right to pi at that point. That gets you halfway there. And then continue on the journey and you'll see where you're at. All right, so now we have a sense of the nature of this. Now, what we figured out earlier was where the graph would hit the pole. That's going to happen on the 2 pi over 3 to 4 pi over 3 interval. All right, so let's actually take a look at that. Two pi over 3 to 4 pi over 3. You'll see that that gives you just the inner loop, because that's where the inner loop begins and where it ends. All right, so we're starting at 0. We first hit the inner loop. I can make a note of that. We first hit the inner loop when theta is equal to 2 pi over 3. Then we work our way through the loop, and then we come out of the loop when theta is equal to 4 pi over 3. And then we continue our way on to 2 pi. All right. So now that we have a good sense, or at least hopefully anyway, that's the plan, by exploring on the calculator a good sense of the nature of the graph, now we can dive into the area and the arc length. So let's focus on, again, the area first. 1/2 r squared d theta. Well, we have an r. That's great. We have an interval, kind of, sort of. But then that's really it, all right? So the one thing you do not want to do so this is a big no-no. I'll write out the incorrect integral, and I'll tell you why it's incorrect. So from 0 to 2 pi, let me actually use legible penmanship. One half the r squared d theta. All right, with the r being 2 plus 4 cosine theta. All right, that's a mechanical approach. You didn't think at all, and in doing so, you came up with something that will be utter and complete nonsense. All right. And honestly, you'll get what you deserve because you didn't study. That's why that happens. All right, it's kind of like volumes of revolution. I remember that from Calc 2. The disk method and the washer method and all that stuff. It's like, all right, I got a formula. I know I got to put the function in here somewhere. I'm just going to dump it in and hope I get some kind of partial credit. So you got some partial credit, but you didn't get full credit. Why? Because you didn't really know why it worked the way it did. All right? Let's see if we can figure out why it works the way it does. If I go from 0 to 2 pi, remember, we're talking about infinitely many of those little circular sectors, all added up. If I go from 0 to 2 pi, I'm going to grab the circular sector going the full length all the way around. I'm going to keep going. And then I'm eventually going to get to theta equals 2 pi over 3. All right? Then I'm going to double count that inner loop. All that area in there is going to get recomputed because the next part of the process is going to have that integration formula is not going to stop. This is still part of R. It's going to account for all possible areas between the pole and the curve. So it's going to figure out the area of all of this in this inner loop and add that on it also. And then it's going to keep going back around 4 pi over 3, continuing on all the way up to 2 pi. So what it's going to do is it's going to do a complete double count of that inner loop. All right, and that's going to be a problem because we're going to get an area that's way too much. All right, so in terms of area, I don't want that inner loop to be double counted. Whereas for arc length, I want that length to be accounted for because if I got to run around this track, I'm not a big runner, as you probably imagine. So I want every step accounted for. So if somebody's like, yeah, so you ran 5 miles. I'm like, no, I ran 5 miles and 37 feet. You're gonna give me every freaking foot that I ran because it was torture for me. Like if we can go to the nearest like 1/4 inch, we would do that too. Like you're gonna give me everything. We're gonna know how much I ran. All right. For area, it doesn't matter. We just want the inner region. So we don't want to double count that. So what we're gonna do is find the area going from 0 to 2 pi over 3. Of 1/2 r squared d theta. And then we're going to add to that the area going from, it's not working as well as I want, going from 2 pi over 3 to 2 pi, 4 pi over 3 to 2 pi. Of 1/2 times 2 plus 4 cosine theta squared d theta. And we're going to get the sum of that. And we're going to ignore the inner loop. We're going to pretend it's not even there. Because all we would end up doing if we found the area from 2 pi to 4 pi, 2 pi over 3 to 4 pi over 3, is we would be double counting it anyway.
Did you know what those numbers
Which one's the 2 pi over 3 or 4 pi over 3?
Yeah.
Oh, so this is all unit circle related. So once we got cosine of theta equals -1/2,
Yeah.
on the unit circle you're just looking for x values. As the coordinates, the x values are -1/2. The angles that go along with those.
Oh, okay.
So it's all unit circle.
At this point, we still don't know. We are just assuming it's 2 pi over 3. Or is it, do we know definitely it's...
We know definitely it's 2 pi over 3 because that brings us to the pole. Okay, because when we start here, we hit the pole at 2 pi over 3, that's the beginning of the inner loop. And then we hit the pole again at 4 pi over 3, that's when we're coming out of the inner
Because
loop.
we plugged it into the calculator?
Because we did this work here.
What kind of supply link for lap model?
What's that?
Were those graphs plugins the one that
Limason?
Limason. So this only applies with Limasons, like you don't have to worry about.
You don't have to worry about an inner loop for anything else.
Just Limasons?
Just the Limasons, yeah.
Okay.
Could you alternatively do the whole formula and then subtract out the other loop?
Absolutely. Yeah, so if you did 0 to 2 pi, got of the same function, and then subtracted off of that 2 pi over 3 to 4 pi over 3, same thing. One way or the other, you got 2 computations ahead of you. All right? But the good news is, again, you're looking at 2 pretty hairy integrals here, right? Like if you had to do this by hand, you'd have to actually use a double angle identity for cosine in order to simplify it, because cosine squared is not easily integrated. When you distribute that out, I promise you, it's a mess. Right? You believe me, and we move on. So we type this into our calculators, and we're just thankful. Let me just get out of here because now I'm just like stumbling around. All right, so math 9. Zero. And I'm going to put the 0.5 open paren. 2 plus 4 cosine theta.
How'd you get that 0.5?
Oh, the formula is 1/2 r squared d theta.
Right, but how'd you get that there? Like, how'd you in the calculator?
Oh, I just typed 0.5, like the decimal point. Now, how did I get the function itself?
No, like.
Let me see, because
As well as type
oh,
Should we just
oh, just do it in. You'll have to use double parentheses. Yeah.
Oh.
Alternatively, put the 0.5 before you bring the integral function up because it's coefficient. So d theta. Gotta get my upper bound in here of 2 pi over 3. Now, normally I would say, let's just do it all in one shot, but I don't want to type all this stuff again. So what I'm gonna do is I'm gonna hit enter, get that number, and then I'm gonna hit second enter, or you can hit the up arrow on these calculators, but second enter works just fine too. Change this to the bounds that you want. This one should be 2 pi. And this one should be 4 pi over 3. So I have this computation, and then I'm just going to add to it the previous answer. All right, just so I don't have to worry about retyping that hairy decimal. So second negative symbol. All right, so that's in lieu of actually storing it in as a dummy variable. At least not tonight. So 1/2 r squared d theta. Looks like my structure is correct. My bounds look good. 0 to 2 pi over 3 for the first one. It gave me a 17 and change. The second one, 4 pi over 3 to 2 pi. I'm taking that and adding it to the previous answer, second negative symbol. I'm going to hit enter, and I'm going to get that number, 35 and change. You might take a look and see if it's some multiple of pi, just to see if there's a way of writing it as a clean answer. Otherwise, just put the rounded answer down. So I'm going to divide it by pi. It doesn't look very clean. I'll try math fracking it. No, it's not going to be clean. So 35.525 is what we're settling in on, approximately. And I hit enter again for some reason, I don't know why. All right, so try it on yours, because again, this one I'm still just getting used to. It's entirely possible I hit something terrible.
Let's see.
35-ish? 35.525, something like that.
Yeah.
Because I'm worried that I messed up, so.
I tried that.
Oh, what's it? They just bought it.
So I brought this to 1/2.
6.7.65.
I feel like I'm missing a coefficient now that I'm looking at yours. $7.5116. That feels right. Mine. The reason I'm pausing is because my number feels absurd. So Not the
No, I
same.
took, I just took,
And then I got the same answer.
Oh.
You got the same answer. Yeah, that actually would make sense if they were the same answer. Huh. I mean, I guess I'm kind of rooting for my answer.
I think you actually have to see this.
Well, if this were a circle, it would have a radius of around
Oh,
6.
I think the square is supposed to be on the inside of that first thing. On the bottom one. Or both. I think it's squaring all of the entire.
I did the subtraction and I got the same thing. You got 35 points something.
You got the same
Yeah.
thing as me? Okay, so I think it might be alright. Now I'm wondering about you.
You're supposed to just do both of them and add them together.
Yeah,
I got 13.79.
you got 13.79 ish. Damn it. If it were a circle with a radius of 3, yeah, because diameter is 6 roughly. Radius of 3 pi. Yeah, 35 just seems so large.
I think you're right. That's what I got. 35.5.
35 foot better.
Yeah, that's exactly what I got. I just forgot to square it last time.
Yeah, I'm not seeing anything wrong. Yeah, this looks right. How do you scroll? Oh, hit enter,
Oh.
and then you can scroll over. Oh, okay. You only have cosine squared. You want the whole shebang squared. 2 plus cosine. You gotta close it up for cosine, close it up for the function then square. So you want your power of 2 to be after that. Because for whatever reason, cosine theta close parentheses squared on your calculator is just the cosine being squared.
Oh.
So you actually have, those calculators have to have a double parentheses in order to make it work.
Oh, that's what I did. I noticed that.
All right, so we're gonna live with the 35 and change, at least for now. And then if anybody comes up with a mistake on that, then it just feels foolish. All right, now the good thing is for the arc length, you don't have to worry about really anything that we were concerned about for this part of the problem. All right, so that's the great news. All right, so and you'll find that that's the case for a lot of topics where there's a lot of minor details that could throw you for a loop if you're looking at it in one regard, but then it simplifies a great deal if you look at it in a completely different regard.
So it doesn't make completely correct. You know, I'm just drawing the other work.
Correct. Yeah, I don't want to see anybody trying to integrate this by hand, right? Because then I'll have to grade it, and then I'll have to take off points for stuff that I don't value in this course.
That's what I'm talking to.
Yeah, exactly. Now in Calc 2, I'd emphasize it and I'd penalize and all that stuff, but in this class, it's not something that I'm looking for. All right, so for arc length, straight from 0 to 2 pi, the sum of the square values. So r, which is 2 plus 4 cosine theta squared, plus the second part is a little hairier. You need the derivative of r as a quantity squared, d theta. All right, so I just need, so here's my r right here. I just need the derivative of this. Constant goes to 0. What's the derivative of 4 cosine theta? give you that. -4 sine, yeah. Now, for this one, you could do some simplifying before you get hot and heavy into the calculator, but it's not really necessary, it's just up to you. It's just if you do the simplifying, you could find yourself with a beautiful identity that could make what you have to put into the calculator that much easier. So let's go down the rabbit hole a little bit, but if things start getting out of hand, then we know that we have a bailout. The bailout is math 9 in your calculator, all right? So distributed property on the 2 plus 4 cosine theta is going to be 4 plus 16, because you're going to have the outers and inners, so you got to FOIL it out. So 8 cosine twice, so 16 cosine theta plus 16 cosine squared theta. Then if you square the other part, you're looking at a 16 sine squared theta, so plus 16 sine squared theta. Now this identity we're going to be working with fairly frequently in this course, so it's worth taking the time to reinforce it now. Let me get rid of the calculator for a minute. All right. We know that cosine squared plus sine squared is equal to 1. This is just a constant multiplier of that. All right, so what I can do is factor out a 16, and I'll have cosine squared theta plus sine squared theta. So that's what this part is equivalent to. And cosine squared theta plus sine squared theta is equal to 1, so it zaps away. All right. For this particular problem, do you need to do that? Absolutely not. You just take that top red line and just chuck it in your calculator and get an answer and call it a day. But for the sake of future self, it's worth looking into, because down the line, when that technique is necessary, you're going to be thinking, wow, I'm glad I'm used to that by now, right? Because it won't be a thinking part of the process. So the common factor of 16, we yank it out. Cosine squared plus sine squared is equal to 1, so we just cancel it away. So then we have some like terms. The 16 and the 4 can go together to give us a 20. So 20 plus exactamundo. And so at a minimum, we have something much easier that we could type into our calculator. And that's all for this kind of problem. That's all we're looking for. We're not looking for anything more elaborate than that. We're just looking for something that's nicer to type in. All right. Later on, we'll be looking for even more, but for now, not the objective. So, math 9 on the interval of 0 to 2 pi. Let me just chuck in the 2 pi. Square root of 20 plus 16 times the cosine of theta. Close it up. No power. That's something. Call that a win. So you'd have double parentheses all over the place if you had that first expression that you typed in. All right, so here's hoping. We're looking at something in the neighborhood of approximately 26.73. All right, not overly concerned with rounding in this course. So however you round, that's fine by me as long as you round it correctly. Because the one conversation I'm hoping to never have again, it's such a weird conversation. You said it didn't matter how we rounded. Why did you take off a point? You're like, well, I took off a point because you rounded to the nearest tenth. You just didn't do it right. Now you can round any way you want. You just got to do it right. All right. So that's the important ingredient. So that, as long as you have that in mind, I think you'll be okay. All right. So answers in exact form, that's a different story, but I wouldn't worry about that too much. All right. You'll be surprised. There'll be some questions on the first unit test where you'll be like, "There's no way this is the right answer. It's hideous. It's the right answer." All right, because you went in decimal form. It's perfectly fine. If you wrote it in terms of pi, it would be much nicer, but it doesn't get you any more credit. All right, so Papa Star on number 3, whoever Papa Star is. And that's going to be part of your homework. We'll go over that next class. So that's it for tonight. If you have any questions, stick around. Otherwise, have a wonderful evening, and I'll see you on...
You say you're going to take out points for decimal positions? Because mine is giving me 1 decimal point there. I'm getting 26.73. Is that okay?
It's giving you 0.7...
That is.
Oh, you took a staple?
Oh.
Yeah,
It's just down to
yeah, it's fine if it's
Okay.
right there, yeah.
This is the only thing I can get.
For the first unit.
The first unit?
7.7.
So we just like this one.
Yeah, we're gonna get more packages, yeah. That's part of the fun, I guess. But fortunately, we have calculators, so you know, as long as you never forget that, then I think you'll be okay. All right? So the r equals 3 is a circle with a radius 3. The other one, if you happen to recognize that as a lemniscate, then wonderful. But again, because you have a calculator, you don't officially need to recognize it as a lemniscate. Because the calculator is going to set you up. The domain is given, so that's good. So I'm going to type in the equation. I'll type them both in. So r equals 3. R equals the square root of 9 cosine 2 theta. And this is happening over the interval of 0 to 2 pi. So I'm going to go to Window. I'm going to make sure my thetas are appropriately adjusted. And you know what? Actually, let me not do that. I'll go back to y equals. I can't do it on this calculator. Try Zoom Standard or Zoom Box first, and then go back into the window and change what needs to be changed. Because you'll have to worry about the x's also if you do it this way. I just don't, this type of calculator doesn't have a zoom, so I'm locked into doing it this way. So 0 to 2 pi, a small theta step, so it's nice and curvy. My x min, for whatever reason, it's at -3-ish. I'm going to make it -10 to 10. Same thing for the max, for the y stuff. And then I'll take a look at the graph. And if it doesn't fit all the important characteristics, I'll adjust. All right. Oh, I got a histogram on. Hold on a second here. All right, so based on my parameters, this is what the graph is looking like. All right. Now I went a little long on it, so I don't need to go -10 to 10. So maybe I adjust it to -5 to 5. I never learned how to do that. But, oh wow. That raindrop noise. It's so cool, and I just don't know how to do it. Like, yeah. It's like great. That and like whistling with the 2 fingers.
I can't do that, but I can do it without it. But yeah, I can't do that.
I can. That's all I got. That's if I want a high pitch. I can do like the ordinary, like whistling a tune. You know, that's fine, but I can't do I need to get everybody's attention whistle. Like, and anytime somebody's tried to explain to me how to do it, it never landed.
It's like you don't blow out, you kind of use your tongue to push the air out, so you go.
All right. I'll give that a shot in front of the mirror at home, and then we'll.
Move your tongue forward and make like a.
Okay. Yeah. Okay. Yeah. There might be a YouTube video involved at some point too. Also.
Took me a few months to learn.
Yeah. Exactly. All right. So we have the graph, and so what we need is the area between the two polar graphs. Now, a sketch is a sketch. A sketch is a sketch. A graph is a graph. You know, like if I say graph it, that's talking about on coordinate axes or on a polar graph, plotting points and things like that. But a sketch, the sketch is for your own benefit. It's for the purpose of you being able to get a sense of what's going on in the situation. Now, one characteristic of a polar graph on these calculators that I never have been able to figure out is why it doesn't seem to want to connect. A lemniscate does connect. There is some mathematical aspects of the function itself that would make it seem like there's some contradictions going on. But if I make my theta step sufficiently small, it will connect somewhat.
I don't have that top back one. I'm not in my connector. It's just sort of two. Yeah.
Oh,
Connect.
You have like a little bit more than what we have.
a little bit more?
Yeah, like let's say
Yeah.
that one.
Oh yeah, so that's normal. That's pretty much it trying to say that this is like
It
that.
doesn't move on both sides.
Oh, you just got a circle. Oh no, that's pretty much it. Like it's
It
not.
doesn't join, but it's great.
Yeah, but if you make your theta step smaller, make that like 0.05 or something, it'll connect it even more. But for some reason, it's never gonna fully connect it.
You're right, the .05 is better.
Yeah, 0.05 slightly.
Yeah.
Yeah, and you could get to a point where it gets really, really close, but now you're waiting a half an hour for it to graph. So, like, you just gotta just believe. Did you get rid of the error?
I did, yes. I was doing the top one instead of just graph.
Oh, gotcha. Oh yeah, there you go. So make your theta step something smaller, like 0.05, and it'll work out a little bit better. Yeah, so mine, for whatever, I didn't even change it. It was already pretty small. Mine was already like 0.01-ish, 0.02. So that's why mine was a little bit more complete than yours. But I could do, see, I can, because it's going to graph it instantaneously, so I can go a little crazier. Hopefully, you see.
Oh, that's perfect.
But it would take a solid like 5 minutes for your graph to process that, or your calculator to process that. So it's a little bit nicer, very motionless. So we need everything but the glasses. Area between the polar graphs. So outside the lemniscate, inside the curve itself. So we got Spider-Man's mask. We don't want the eyes, we want everything else. All right. So that's really what we're looking at. So the big question would be, okay, that's wonderful. How do we get that? Let me get this. Oh, there's a share option here. Hold on, let me see what that's all about. Copy. Can it be that easy? Of course not. Because why would it be? Long pressed, paste. Oh, wonderful. It gave a link to iTunes where I could possibly find that graph and calculator page. That's so useful. All right, do it the old-fashioned way. Save the photos and then import the photo. And it's ginormous. It should actually be all right. Yeah, I think it's fine that size. All right, so on your end, just a rough sketch on paper is fine. but for me, I have the ability, so why not, right? All right.
Is that the outer part, is that a circle or is it a ellipse?
It's supposed to be a circle. I could have made it look more circular, but it looks like Spider-Man this way, so we're going to go with it. Very, very happy to have it like this. Oh, and fun fact, I wrote this problem, but I didn't even talk about it. The theta step, it's giving an indication to make it something pretty small so that it's a little easier to see that it should be connected. But even still, like I had this at 0.001, and it's still not fully connected. So you have to believe that it's going to connect, right? Based on knowledge of what a lemniscate is supposed to look like.
Mine's connected.
Yours is connected?
Yeah.
All right, look at that. Oh, that's beautiful. Oh, okay. So you have it in degree mode and you went 0 to 367.5. That's good.
Yeah. I just want to standard and different. So.
Yeah. That worked. Okay, so the characteristics here. It boils down to a couple of things. I need to find the area of the outer function and the area of the inner function, and logically I think subtracting the two makes the most sense. As far as credit is concerned, like on a test, I need to see calculus in there somewhere. You don't need to do calculus when it's unnecessary though, right? Because I'm never, honestly, I'm not gonna give you a problem where it says, find the area of this circle using the formula, the integral formula. And my reasoning behind that is, like, there is room for elegance. And that would be like, why would I use the complicated approach when I can just use pi r squared for a circle? All right, so it's not gonna be a standalone problem, but if a circle is embedded in another question, you can use pi r squared for the circular part and then use the calculus for the other piece. All right, so that's what we're gonna do. I'm gonna look at, and let me put my toolbar over here. So I'm gonna look at r equals 3, the area pi r squared. So pi times the value of 3 squared, so 9 pi. All right, so that's that. Then I need r equals the other stuff. 9 cosine 2 theta on the interval of 0 to 2 pi. All right. So first thing I want to do is make sure that my domain is appropriate, that I'm not going to double trace this, because if I do, then I'm going to count extra area when I don't want to. And for whatever reason, I put the calculator away, and I shouldn't have, so let me bring it back. All right, so the one strategy to avoid having to handle the algebraic approach was to just dial back your theta max a smidge. Instead of going to 6.28, go to like 6.2 and graph it. It should be just short of complete. All right, so you can see that the circle is just short of being complete, and so is the lemniscate. All right, so that's indicating that 2 pi is most likely the perfect fit for one full loop. All right, again, algebraically you can do it, and I'll talk about that in a little bit, but this is a quick way of verifying it. In fact, you could even get like really, really close, 6.27. Then it becomes an eye test though, so you got to be careful about that. All right, so you'd have to really get in there, and I have the benefit of a touch screen, so I can really do it. A lot more arduous on the graphing calculator, but you could really get close in there and see that it's just a smidge shy of being complete. All right. So the other way to handle it is to actually just do some algebra, or well, really pre-calc. Right. So what I would say is this picture, it's going to run the distance from 0 to 2 pi. So what I would do is test 0 and test 2 pi and see what R values come up. All right, because in theory, that should represent the beginning and the end of the journey. All right, if it's a closed loop, the beginning and end of the journey should be at the same location. All right, now you kind of reason it out, you're dealing with cosine at 0 and 2 pi. They're both on the x-axis. Odds are it's going to be the same value, but you never know. So pop it in, 9 cosine, come on, cosine of 2 times 0 and then 9 cosine 2 times 2 pi. That's what I was saying, it's more pre-calc than anything else. It's not algebraic manipulation as much as it is computation related to trig. All right, so 9 cosine of 0 for the first one. Cosine of 0 is equal to 1, so we're looking at the square root of 9. Now this is the principal square root, so that's just a 3. Principal square root is just talking about whatever the sign is associated with the radical is the sign that applies to the final answer. The only time you get to throw the plus or minus in there is when you introduce the radical. I mean, that's something that's old news, but I find that I can never say it often enough because people tend to lose sight of that thing. Because they look at it and say, well, what about negative 3? Well, it doesn't apply because this is the positive square root. All right. 9 cosine of 4 pi, cosine of 4 pi is at the same location. So it would give the same value. So this is actually going to be the same exact thing. The square root of 9 equals 3. All right. Both of these are calculator friendly. So if you were to go into anything that's on coordinate axes for the unit circle, or anything like that would be calculator friendly. So just pop it in and show that they're both equal to 3. So this indicates that there's a closed loop and so therefore we have a good domain. All right. Now we want to use our 1/2 r squared d theta rule to come up with the area over this interval. Let me show you a couple of ways to do it, and then we can kind of pick and choose which way makes the most sense. It's going to be the same integral in both cases, but let me just kind of take you down a couple of different roads, and then we'll decide as a group which way makes the most sense. So one way to go about it would be to say, all right, let's just go after it and say that the area is going to be over the interval of 0 to 2 pi, 1/2 r squared d theta, and that r is a specific value. I hit the wrong thing. Well, a specific quantity, in this case, the square root of 9 cosine 2 theta. So that would get popped in. So 1/2 of r squared is really going to be 1/2 of, well, I'll write it in radical form actually first. I'll show the intermediate step. 9 cosine 2 theta squared d theta. But then the radical and power of 2 are going to cancel away. Now, you could pop this right in your calculator right away. I wouldn't do that because you're going to type in more stuff than is necessary. In fact, this actually cleans up kind of nicely because the radicals would cancel, undo. Radical would cancel with the power of 2. And then you can multiply the 1/2 by the 9. So we're looking at, over the interval of 0 to 2 pi, 9/2 cosine 2 theta d theta, which is going to be an easier thing to pop into your calculator. Like, I'm not even thinking in terms of doing the integral by hand. I'm not trying to make it convenient to do this by hand. I'm making it convenient to type it in. All right, so that's something that's really important to keep in mind. All right, we want it to be calculator friendly. So math 9 type in your font. I'm just going to write 4.5 cosine 2 theta d theta going from 0 to 2 pi. All right, I'm going to hit enter. And we're going to get that number. Well, you might get something different on your calculator. Mine is just being what it thinks is extra precise. It's coming back with an answer of 0, basically, which can't possibly be correct. All right, because there is an area, there's a noticeable area there. All right. This is saying, with the scientific notation at the end, and in fact, it's very easy to miss this, so you got to really be careful. 6.975, you're looking at that and saying, okay, well, it's as good or as bad as any other number related to area. But the E negative 16 is telling you to move that decimal place to the left 16 units. So this is 0.15 zeros, 695, 6975, etc. All right, so damn near 0 is what it said. Can't be right. The reason why is because what we did was actually a common Calc 2 issue. Parts of this area is going to be positive and parts of it are going to be negative. All right? So let's just actually take a minute and investigate which parts would be positive and which parts would be negative so that we can use this as a technique from here on out. The good news is you don't have to go back and recompute everything by hand for, hours upon hours, because all we have to do is hit second enter and change the balance. All right, so let's go, because we're looking at 4 congruent parts here. Let's go from 0 to pi over 2. All right, and I'm comfortable going from 0 to pi over 2. Let me just make sure that I am comfortable doing that. Actually, pi over 4, I think. Because I want something that's going to zero out. Pi over 4 is what's going to zero out. Because that'll give me cosine pi over 2. So, pi over 4. So that's just the top part of the right lens. Right? It also gives me some part of the circle, but I don't really care about that. Right? So I'm just looking at this one piece. So you would think that's the first quadrant value, that's going to be a positive measure. So let's see what the calculator says. Instead of 0 to pi, let's do 0 to pi over 4. And we get 2.25. All right, so I can make a little note here. So just this part, right in this neighborhood here, this part is 2.25. All right, so then I could keep going with this. I could take a look and see, okay, well, the next interval and the one after that. But at this point, I think you kind of have the idea that if you know that there's 4 congruent pieces, why not just take that and multiply it by 4, So what I could do next is, just kind of play around with it and see what would happen graphically if I went from, let's say, negative pi over 4 to pi over 4. Actually, let me not do that. Pi over 4 to 3 pi over 4. I hit clear accidentally. Because I was going to say negative pi over 4 to 3 pi to pi over 4, but then I forgot that it's a 0 to 2 pi domain. So 3 pi over 4. You take a look at that picture.
0 to pi.
0 to pi.
Yeah. It doesn't move crisscross.
It does. Okay. Right. Okay. That's good. So then 0 to pi in our function, which is like jumbo sized for some reason, 0 to pi it's going back to 0. All right. So, and again, like, I've been working with these calculators for years, so I look at that and immediately 0 pops into my mind, which, you know, like, is kind of unfair, because if you're not used to these calculators, you look at that and maybe you miss the e -16, and you're like, well, this kind of sucks because I don't see 0 when I see that number. But basically, if you see e with a negative number, start thinking more like 0. All right. So it zeroes out if I take the 2 top hats. So now we're thinking, wait a minute, this isn't like Calc 2 in the sense that anything above the x-axis is going to be positive area and everything below it is going to be negative area. You know, you could be looking at it as, well, maybe it's to the right of the y-axis, or to the left of the y-axis is negative, to the right of the y-axis is positive. All right? But you can also be looking at it in a different way, and this is the weird part. So my calculator is annoying because it will not show the tracing of the graph, and lemniscates are just generally annoying because they don't really show you the graph being graphed as it should be, right? But let me just try to get that across to you here. So
Shift the graph like 3 to the right.
you could do that, but I think that anytime you shift it off of the axis, off of the pole, you're making the math more complicated. Generally, you want to shift it to the pole so that you can make it a little bit simpler, right? And the rationale is because this formula is defined as, with the 1/2 r squared d theta, that r is defined as the distance from the pole, right? So anytime you move off the pole, things start getting really complicated, all right? But let me show you, just using arrows, how this would be drawn if the calculator did a good job of showing you the actual curve being plotted, or you did it by hand. All right, you would start off here, and then you'd work your way around in this direction. You blast right through the pole, and then you continue on. And then you'd pick it up over here through the pole. All right, so, and I'll tell you right now, like, I did not pick this up until I started teaching this course. Part of the plot is going counterclockwise and part of it's going clockwise. The part that's going counterclockwise will yield a positive area. Counterclockwise gives a positive area. Clockwise gives a negative area. Counterclockwise gives positive area. Clockwise gives negative. Now, it's one of those things, like, you get bogged down in the process, the procedure, and you kind of lose sight of some things. And the reality is a polar graph is just an augmented unit circle. Unit circle, in the unit circle, you go counterclockwise, that's a positive angle. If you're going the other way, it's a negative angle. All right? Then when you look at the integral formula, it's 1/2 r squared d theta. All right? Seems like notation, but really what are we doing? We're taking 1/2, we're multiplying it by r squared, and multiplying that by a change in an incremental change in theta. If theta is going in a clockwise direction, theta should be positive. If it's going in, counterclockwise direction, theta should be positive. If it's going in a clockwise direction, theta should be negative. All right, so what that tells me is when I create a graph, what I want to do is look for the part or parts that are moving clockwise throughout the domain. So we're starting off on at 0 radians and working our way to 2 pi radians. On that interval of 0 to 2 pi, identify the pieces that are moving in the counterclockwise direction. Those are the pieces that you should use for your area. Otherwise, you just have to do it a piece at a time and negate all the negative ones to make them positive. All right? So what we got from this is that this will zero out, equals 0, so this is no good. Better would be going from 0 to pi over 4 and then multiplying it by 4. So that's going to be 4 times 2.25. So 9. All right. Now, a good question that I don't think has been asked might be, where the hell did you come up with that pi over 4? I'd be asking that.
Well, not the bio. Why are you using the 4 just because you saw the graph?
Because I saw the graph, yeah. 4 symmetrical pieces.
Why don't we just go from 0 to pi over 2?
0 to pi over 2.
And do 3 pi over 4 back to 0.
Well, if you do 0 to pi over 2, that's going to give you some negative area.
We stop right in the center, right?
No, pi over 4 gets you to the center.
Oh, pi over 4.
Yeah, it's really weird. There's actually a lot of points that happen in these little parts that get connected. That's why there's such a gap there, because if you have a theta step that's too big, it's skipping over a lot of points that would be plotted there. So there's actually a ton more points that get plotted in that little intersection with the polar axis that just get glossed over when you have your theta step too big. All right. So the key here is knowing where it crosses the pole. All right. So determine where the graph crosses the pole. That'll give you your pi over 4. So that's taking our original function, our original r value, 9 cosine 2 theta, and doing one of two things. Guessing and checking away, or set it equal to 0 and solve. All right. The reason why I was able to come up with pi over 4 so quickly was because I know my unit circle to the point where, well, it's ingrained, so that's not fair. I've been doing this long enough. But cosine will zero out if it's on the y-axis at pi over 2 or 3 pi over 2. So I was just thinking, well, what would 2 pi have to be in order to result in a pi over 2? The pi itself would have to be, the theta would have to be pi over 4. All right, but okay, we don't like that. So we square both sides. 9 cosine 2 theta equals 0. Divide out the 9 cosine 2 theta equals 0. You're still going to have to know a trig fact in order to get this. All right, so whether it's an identity, I mean, you could apply an identity. I just think you make your life a little bit more complicated. The better way of handling this is to define a dummy variable, or, maybe not, but this is what most people do. Let a equal 2 theta. And so cosine a equals 0. And so we think in terms of the unit circle. That happens when a is equal to pi over 2 and 3 pi over 2. And a bunch more other possibilities, but we're just staying in that domain for now. And then once you figure out that piece of information, we replace the a with what it really is, the 2 theta. All right, and so you get theta equals pi over 4 and 3 pi over 4. And I want the first instance where it goes through the pole, so I grab this one. All right. So that's all, if you're thinking high school, algebra 2. or college algebra or trig. But yeah, I mean, the way around it is to say, all right, well, I got some unit circle values. You work your way around and you start guessing. All right, is that enough? I tried pi over 12, not enough. All right, pi over 6, not enough. Pi over 4, oh, look, bingo. There we are. And so you can avoid the algebra too.
Why is it that when you put it in the calculator and you put the pi over 2, it still doesn't like quarter?
Because it's, oh wait, it's still only giving you a quarter?
Yeah.
Maybe I didn't even get that.
So window.
Yeah, because what it's doing is it's plotting infinitesimal points on the other side of the pole. You just can't see it. Because
Okay.
it's plotting them super tiny. But it's all there. All right, and so we do have to state what the final answer is, because after all this work to come up with the glasses, it's easy to lose sight of the mass. So we had 9 pi for the circle, and so 9 ended up being the total area contained within the glasses, the lenses. So the solution, the final answer, would be 9 pi minus 9. Talking about the first quadrant in the rectangular system, which corresponds to the same quadrants in the polar system. All right, so 0 to 90 degrees is your first quadrant, and then so on. All right, so we need these graphs, but 4 times the sine of theta, 4 times the cosine of theta, those actually, believe it or not, are just circles. All right, your calculator will tell you that pretty easily. It's just a question of what their centers are. And so I could plot them, but I don't really, I mean, on my calculator, I don't think it's going to serve much of a purpose, because, oh man,
0, 2, 2, 0.
I got a stain on my shirt. What did you say, sorry?
The graph is 0, 2, 2, 0.
0, 2, and 2, 0, yeah, the centers, exactly. So the leading coefficient in each case is going to give us the diameter of the circle, and the function itself is going to tell us where it's living. All right, so the sine function is going to live on the y-axis, and the cosine function is symmetric about the x-axis. And the 4 gives us diameter. So that, whatever that leading coefficient is, will indicate your diameter. So from that, you have some pretty useful characteristics of your circles. I mean, the first and foremost would be the fact that they are circles. So you would need to know that. But again, the calculator will help you out. And in each case, I'm going to plot the center. Undo, it's a little off. Still a little off. There we go. All right, I just need some more detail to it, because if this were the XY coordinate system, then I could just count boxes. I could be like, well, I got to go 2 up. You're like, oh crap, where's 2? You know, how do you get 2 up? Well, these 2 circles are going to intersect each other. So that's something. Let's do that. Let's figure out where they intersect. So 4 sine theta would be equal to 4 cosine theta. That's for the intersect. All right, 4's cancel, so sine theta equals cosine theta. And there's many instances in the unit circle and beyond where sine and theta are equal to one another, but there's only one that happens in the first quadrant. It only happens, and again, first quadrant. The relevant value would be that theta is equal to pi over 4. All right, so r equals 4 sine theta. R equals 4 cosine theta. I'm going to evaluate each of those for pi over 4 cosine theta. And what is the sine and cosine of pi over 4? Root 2 over 2. Good. Good. 4 times root 2 over 2 in both cases. So normally when you're dealing with trig, you want nice simplified radicals. So in that case, I mean, we could say 2 root 2, but we got to plot this. So let's get decimal. I know that root 2 is roughly 1.4-ish, so roughly 2.8-ish. Since I'm plotting it, 2.8 is good enough because I'm not going to be able to distinguish between 2.8 and 2.82, blah, blah, blah. So we'll plot. Undo, don't need that. So at the 45-degree mark, I'm going to go out almost 3 units. So 1, 2, I guess that's fine. Yeah, I'll just live with it. All right. So the curve, something like this for the sine function, and then something, I kind of lost it here, so let me just plot it again. Something like this for the cosine. Now there's more to it. You can plot it all if you want. Like good looking circle, good looking other circle, wonderful, all irrelevant. All right, so I'm only going with the stuff that actually matters for the problem. So I have a sketch of the important characteristics, and I'm saying area outside of the blue graph, so beyond the blue graph, but inside of the red graph. So basically it's saying everything in the red except for the sliver. All right, because I got to be outside the blue, so anything beyond the blue, all right, and then, but also be contained within the red. So that's excluding this little sliver. So I'm going to do the semicircle. That's r equals 4 cosine theta all right, but only half. I'll just write top half only. All right, and then once I do that, I somehow have to figure out that sliver. Now, like I was saying for the last question that we did, the calculus has to be in there somewhere. Honestly, I don't care where it is. It just has to be in there somewhere. So we'll use the calculus to find this area, I guess. I mean, we don't really need to. We could use the pi r squared, and then use pre-calc to figure out this piece. Or we could go the other way around, use pre-calc to figure out the area of the semicircle, and then use calculus to figure out the area of the sliver and then subtract. but the calc has to be in there somewhere. So it's just a question of what you find to be less challenging. Honestly, I think it would be a royal pain to try to figure out that sliver using the calculus, but it would be pretty easy to do it with pre-calc. All right, so that's the avenue that I'm going to pursue. So what I'm looking at here, and it's kind of hard to see based on a hand-drawn diagram. It's really, really very much a pain. So geometry, maybe a little bit of trig, analytic trig more than anything else. So we have a right angle here just visually. So the central angle of the circle is a right angle. This piece here is known as a circular segment. I think it was last class that I reviewed circular sector. Maybe it was 2 classes ago. And that's where our area formula came from. That was the 1/2 r squared theta. The circular segment has an area 1/2 r squared times theta minus the sine of theta. All right. So that theta in this case represents the central angle. All right, so the area, because we know the radius is 2, of this, just this one piece would be 1/2 times 2 squared pi over 2 minus the sine of pi over 2. So 1/2 times 4 is 2. Pi over 2 minus sine of pi over 2. Sine of pi over 2 is equal to 1. So this simplifies down to pi minus 2 if you distribute it. All right, that's 1/2 of the sliver. Hold on, come on. So 1/2 of the sliver. So if I want the whole sliver, multiply it by 2. 2 times pi over 2. Pi minus 2. And I'll leave that like that until I know what I'm using it for. All right. The other part is just coming up with the top half of the circle. Right? So the one issue that's going to be in play here is just knowing where half of that circle is. You know, it's logical to assume that we're talking, oh, it's probably too small, sorry. That we're talking about 0 to pi, because one full trip around the circle would most likely be in a 2 pi domain, but you want to make sure that you're not just throwing out nonsense here. So very quickly, without doing any work, you could just plug and chug and see. Because 0, if I plug in a 0, it should give me the starting point of the top half. And if I plug in a pi, it should give me the end point of the top half. Otherwise, I'm looking at something else. All right? So 0, cosine of 0 is 1. 1 times 4 is 4. So that's good. But then if I plug in a pi, I'm going to get a negative 4. All right? So that's a problem. All right? So that means that it's not getting to this location at pi. It's getting there most likely before it. Because if I plug in a pi here, and that gives me a negative 4, just think about how you plot your points. All right? The negative is telling us, well, if I plug in a pi, that's putting us over here, but the negative is telling us to go away from that angle. So I'm taking 4 steps away from it. It's putting me right back to that location. All right, so it's seeming as though that this loop will be closed in a pi domain. All right, so what we could do, take a look at our picture and see what's going on there. All right, because I grabbed it 0 to 2 pi just out of instinct. Like, why not, right? But look at what happens when I change it to pi. It's the same picture, which means I double counted the curve. All right? So what's happening is when I put it in 0 to 2 pi just out of habit, it went around the circle once and then it went around a second time. All right? So if I dial it back from pi just a smidge, let's just make it like 3.13, and then zoom in like the Dickens here. You could see that's not what I wanted. You can see that there's a little tiny gap showing that it's just coming short. All right? So you could play around with the calculator, you could play around with the graph until you come up with the right domain, or you could set it equal to 0, because if r is equal to 0, then you know where you stand. It's supposed to go through the pole. Set r equal to 0 and solve, you'll get pi over 2 that way. All right? But I'm trying to give you multiple options here. Long story short, too late. What we're going to do is we're going to find over the interval of 0 to pi over 2, because if we're getting the full circle in pi radians, then we're going to get the top half in pi over 2 radians. 1/2 r squared, my r is 4 cosine theta, d theta, one half r squared d theta. Clean it up a smidge if you want, but this one I think you could probably just type in. I don't think the effort spent on cleaning it up is going to save you too much time. So math 9, 0. We got the 0.5, open paren, 4 cosine. I hit mode accidentally. 4 cosine theta. Close them up twice. For me anyway, it's probably nicer on yours. D theta. Get my upper bound. Pi over 2. Got my parentheses in good, please. You see everything? So 6.28. I mean, it's pretty much screaming 2 pi at us. All right. So, and just bear in mind, folks, we didn't do this to get the answer. We did this to satisfy the need to have calculus in our solution. All right. Because we knew that this was a circle with a radius of 2, pi r squared. All right. So we already knew it was 4 pi, chop it in half to get 2 pi. All right. So that's something to keep in mind. Like, it's nice that the calculator gave us a value, but we already knew that value. We just needed to check the box to get calculus credit. All right. So I have the upper half of the circle, so the semicircle. The whole sliver is 2 pi minus 2. So my final answer, or at least is going to shape up this way, final. We're looking at 2 pi minus 2 times pi minus 2. But that could even clean up a little bit further. 2 pi minus 2 pi plus 4 so we get a result of 4 after all that. So 4 square units. And complete inconsistency in the sizing of my writing. The title is or is not in terms of the grammar. It's pretty clear what we're trying to do here. The issue is, just like with parametrics, we want to be able to find a derivative without having to convert the polar function into rectangular form. All right? Because you end up spending a lot of time just on the conversion, and there's no guarantee you're going to be dealing with a nice enough function that it's going to make the calculus any easier. All right, so the first thing we're going to do is learn what the rule is for finding the derivative of a polar function. Now, I'd like to believe that after I show you this, you're going to come away with the thought of, okay, I'm never going to memorize that formula because I now know where it came from, because the formula is gross, all right? But you'll have an index card for the first test, so you're just going to write the formula down on that and forget everything that I'm saying. But worst case scenario, like, it really is not terrible to invent this formula, all right? So I have this nice diagram here that I stole from some online resource somewhere, but really it's just getting across the idea that, yeah, you could have a polar graph, and with that polar graph, you could have tangent lines, and you could have normal lines. Normal is just the perpendicular to the tangent, all right? But we're thinking in terms of R and theta, not in terms of X and Y. But ultimately, when I come up with a tangent line equation, it needs to be back in terms of X and Y. So the first thing I'm going to do is note what X is equal to in terms of R's and thetas. X is equal to R times the cosine of theta. Y is equal to R times the sine of theta. And that just comes from unit circle. Sine of theta is equal to y over r, solve for the y. All right. Now, what I can do is I could take the derivative of x with respect to either r or theta. It does not matter. All right, so I'm going to do it with respect to r. But we have to take the derivative implicitly. All right, because the derivative is being taken with respect to r, I need to make sure that every time I take the derivative of the dr term, I'm going to slap on a dr d theta. I'm sorry, a non-r term, I'm going to slap on a d theta dr. All right, so we're looking at the product of two functions, r and the cosine of theta. So here's my first function, and let me make this purple so I can say that here's my second function. Product rule. First times the derivative of the second, so r times derivative of cosine is negative sine, so negative sine theta, but because this variable is not r, I also have to multiply by d theta dr, plus the second function, which is cosine, times the derivative of the first function. Well, derivative of r with respect to r is equal to 1. So I'm just going to chuck in a times 1 just so you know, but it's irrelevant. You don't really need it. All right. So then we could do the same thing, but this time with r and sine of theta. So dy dr, first function, r, multiplied by the derivative of the second, cosine theta, but because we're taking the derivative of a variable that does not involve r, I need to differentiate the theta with respect to r, plus the second function, sine theta, times the derivative of the first function, which again is just a 1, because dr equals 1. All right, so at some point, this needs to become dy dx. So I have a dy dr. I don't want the dy dr, I just want a dy. All right, I have a dx dr. I don't want dx dr, I just want dx. So what I'm going to do is take each of these and multiply them all the way through, multiply them by dr. All And I'm gonna get rid of the calculator for now. So multiply by dr across the board. I think transitioning between apps is what's messing up my pen. All right, but I'm gonna write the second one first because ultimately it needs to be dy over dx. So I'm gonna put this one right here, and that's gonna give me dy is equal. Come on, let me try doing that. dy equals r cosine theta times dr. I'm sorry, d theta plus sine of theta times dr. All right, so just multiplying every single term by dr. Cancels here, introduces here. It's going to be the same idea for the dx. So dx is going to be equal to negative r sine theta d theta plus cosine theta times dr. All right. Now what I need is dy over dx. Oh, it's funny how that works. All right. Whoop. And whoop. And now you have a rule. So dy dx is equal to r cosine theta d theta plus sine theta dr over negative r sine theta d theta plus cosine theta dr. Rolls right off the tongue. So, like just, commit that to memory and you'll never have a problem. Obviously not. All right. So it ends up on an index card that you reference. And then after that, it's like, okay, cool. Yeah. I don't remember that formula, so I just Google it. That's really what it comes down to. But this is the origin story behind it, and you can see it's rooted in differential calculus. It's not anything too complicated. And in fact, I would not be shocked if maybe part of this was a question when you were taking Calc 1. I do that. Some other teachers do that. They take something like x equals just this part, x equals r cosine theta, and says, and the question is, using implicit differentiation, because at that point you're just learning about it, find dx dr. And so you come up with this final answer completely out of context. You never really learned what it was for until you're sitting here, And at this point, you still don't know what it's for, so that's great. All right, but anytime you're talking about a derivative, dy dx, it's the slope of the tangent line. Right? It's always that. It's the slope of the line tangent to the curve at any point along the curve. It's defined in terms of all of this other stuff, which is kind of annoying, but still manageable. All right. So when I go to find the derivative, really I'm just thinking about it as like, okay, I need all of these ingredients somehow from this function. Well, I got some thetas. I got a theta there. I got an r. These d thetas and drs, that's a little bit of a different story, but still pretty manageable. You can work your way through that. So let me get you at least set up on number one. So I have r equals 1 plus the sine of theta. All right. So dr d theta is going to be equal to cosine theta. All right, so now I have a relation or relationship between dr, d theta, and cosine theta. All right, so I could figure out dr d theta when theta is equal to pi over 3. That would be cosine of pi over 3, which, based on knowledge of the unit circle, is going to be 1/2. All right, so I have that part of it. Now, what we want to kind of do is develop a way to get this information into the formula. All right, so I used some algebra to clean up my dy dx, and it made it a little bit more concise than it was, and that's fine. But I don't see any dr d thetas in there. All right, I see a d theta and I see a dr, but I never see them at the same time in the form of the ratio. So a simple way of handling that would be to divide each part of the fraction by d theta. All right, so top and bottom of the fraction, I'll do it this way, divided by d theta. So instead of trying to manipulate my dr d theta to make it fit the formula, why not manipulate the formula so that it fits the information that you have? Because the reality is, you're more often going to be given a situation when you have r equals 1 something, anyway, not necessarily 1 plus sine theta, but r equals something, and when you take the derivative, you're going to come up with a dr d theta. So why not take your rule and adjust it so that it fits that information? All right, in which case, you'll end up with r cosine theta plus sine theta times dr d theta over, same stuff really, just different organization, negative r sine theta plus cosine theta times dr d theta. All right, so when I look at this textbook rule, the r cosine theta d theta sine theta dr, like that's one that people have there, like, oh, it's in the book, it's online, whatever, I'll put that on my index card. But this small adjustment to it makes life so much easier, so why not make that adjustment to the rule and make that the new rule, right? You gotta think that way sometimes, all right? So, now I have a way to get my dr d theta in. I need to get an r cosine theta in there. I need to get a sine of theta, all when theta is equal to pi over 3. All right, so let's do that. A piece at a time. So let's figure out what r is going to be at pi over 3. It's going to be 1 plus sine of pi over 3. So that's 1 plus root 3 over 2. Not the nicest thing in the world, but we'll live with it. All right. Then I also need cosine of theta and sine of theta, but that's all unit circle stuff. Yeah, I mean, it never hurts to just write it down, so why not, right? So cosine pi over 3 is equal to 1/2 sine of pi over 3. We already figured that out. That's root 3 over 2. So these are all the ingredients. So I got my dr d theta, I got my r, I got the sine, I got the cosine. So I'm ready to rock and roll on my derivative. It's just clean substitution. dy dx specifically is the important thing, because dy dx should be in variable form, but because they're saying when theta is equal to pi over 3, I have license to just plug in the numerical values off the bat. So the r value is 1 plus root 3 over 2. The cosine of root of pi over 3 is 1/2, plus the sine. The sine value is root 3 over 2. The derivative, we figured that out, is 1/2 over the denominator. So we're talking negative r, so negative parentheses 1 plus root 3 over 2 times the sine value, root 3 over 2, plus the cosine value, 1/2, times the derivative value, also 1/2. That's something. That's some good looking calculations right there. Nah, it's disgusting. So a little distributive property, a little gap here. 1/2 plus root 3 over 4 plus another root 3 over 4 over negative root 3 over 2 minus 3 over 4 plus 1/4. I don't feel like getting common denominators, so I'm just going to multiply everything by 4. So 2 plus root 3 plus root 3 over negative 2 root 3 minus 3 plus 1. Two plus 2 root 3 over negative 2 root 3 minus 2. Well, it's all divisible by 2, so might as well. 1 plus root 3 over negative root 3 minus 1. And then if I felt like rationalizing the denominator, I could torture myself even more, I guess. I don't want to do that, so I'm not gonna. Let me actually make that look more like a negative symbol. All right, now that's the slope of the tangent line. They said write the equation of the tangent line. Well, that kind of stinks, because the equation of the tangent line, again, in rectangular form, y equals m times x minus x sub 1 plus y sub 1. What that means is that I need the x and y values for this function also at pi over 3. All right, so it's not over yet. Submitted it as a typo. So x is equal to r cosine theta, and y is equal to r sine theta. So we know what the r value is and the cosine value, so we just have to multiply them. So we don't have to reinvent the wheel, we just got to do the work. And then clean it up a smidge, I guess. Not too much. 1/2 plus radical 3 over 4. And then radical 3 over 2 plus 3/4. All right. So, at long last, I could finally state, so this is the coordinate. I could finally state what the equation of the tangent line is. I was going to say final, but it almost sounded like I cursed. The flubbin' tangent line equation. I actually wasn't, shockingly, the one time. So 1 plus the square root of 3 over the square root of 3 minus 1 times x minus my x coordinate. So 1/2 plus root 3 over 4, close them up, plus the y value of my y coordinate, root 3 over 2, plus 3/4. Holy moly. Look at all that. I'll show you the reason why I find this funny in a sec, but I'm surprised I didn't notice this. That simplifies to -1. So put your function in, get the right domain, and then second trace option 2. All right. It'll create a field once you start typing. At first, it doesn't seem like there's anywhere to type the information, but it creates a field. Yeah, it wasn't until I typed in the pi over 3, hit enter, and it said -1. My first thought was like, what? Screwed that one up. And then I realized these are exact opposites. If I factor out a -1, they cancel. So it actually cleans up nicely. But, well, that's one of the reasons why we have calculators, so that's good news. For the most part, the pre-calc world, building up to the point where we develop some fluency, and then once we have that, when we hit unit 2 and unit 3, all of this stuff is going to work its way into every kind of problem. So, imagine in unit 3 where we're looking at a situation where we have to work with parametrics and polar functions while also thinking in terms of vectors, right? So, in three-dimensional space. So we're building towards something here. It just seems very disconnected at this point. All right, but just like everything else, I'm not assuming that you have any experience with this. All right, so could be pretty boring for some of you. If you have experience in a physics class, then you already probably know something about vectors, probably more than we're even going to cover in this course. But I'm not going to make any assumptions. So a vector is a quantity that has both magnitude and direction. So if you're talking about speed, that would be known as a scalar. All right, so speed is a scalar. This is a classic example, even from physics. That's usually where they start. Speed is a scalar. Velocity is a vector. All right, because speed is really just talking about the magnitude of the velocity. All right, velocity is incorporating direction too. All right, but what happens is people use the term velocity in real life as just a fancier substitution for the word speed. It's like, increase your velocity to 96 miles per hour. It's like, okay, you're not using it technically correctly, but we get what you're trying to say. All right. If I'm saying the velocity is 96, I'm talking about a positive 96. I'm talking about 96 miles per hour in the forward direction, all right, or upward direction, depending on the nature of the space, all right. Whereas speed, if I say my speed is 96 miles per hour, it could be in any direction, all right. So it's just the magnitude of that. But we start with something pretty basic. Sketching a vector from point p11 to the terminal point 4,5. So here's 1, 1 coordinate. Point P. 2, 3, 4, 5. I don't need 5 there. 4, 2, 3, 4, 5. And what was the other one? Q? It's usually Q. Yeah. P's and Q's. It's always P's and Q's. All right. So this is a line segment. A vector needs to start at the origin. All right. The tail of a vector is always at the origin. So what I need to do, and it's a very visual approach, and you'll find that moving forward, a lot of the stuff that we're going to cover in this class is more of the visual variety. Like if you could get a sense of the visual characteristics, then things start working themselves out pretty nicely. Right? What I want to do is I want to pin this line segment at the origin using a translation. So I want to pin segment PQ to the origin using translations. All right, fancy word for shifting the points. All right, so if I'm going to shift point P, I'm going to go down 1 unit, and I'm going to go left 1 unit. So what I do to P, I have to do to Q. So down 1, left 1. So my Q prime is going to be here. P prime is going to be now at the origin. All right. The line segment connecting PQ is the vector PQ. All right. No matter where it is in space, that new line segment is the vector. All right. Always having its tail pinned at the origin. All right. So Q originally was at 0.45. But what we did was we did a translation left 1, down 1 of point Q. And that gives me Q prime of 3, 4. So vector PQ, which we denote with a little arrow over it, kind of half an arrow, is represented just by the endpoint of that vector, which would be 3, 4. All right, that's a lot of like fancy notation. A lot of fancy notation, but really it's just saying, move the points over, find the endpoint of the new line segment, that's your vector, right? Taking on the values of the original coordinates, PQ, right? Now, you may be familiar with another form of the notation, alternate notation. You might see hard brackets 3/4, or you might see even curved brackets 3/4. They mean the same thing. I don't plan on using that notation in this class, but you walk into a linear algebra course. I don't know how many of you have experience with that, but if you walk, like next semester, let's say you take linear algebra, you're going to learn about vectors again, fun fact. But they're going to use that notation because that's matrix friendly. All right, these create column vectors which go right into a matrix. All right, so you know you can get the properties and characteristics down from this course, but you'll have to get used to new notation.
Oh, so it's an X, Y, Z, or X, Y, Z, it's X, Y, Z.
Exactly. Seemingly to make things as confusing as possible. really. It just fits with the operations involving matrices that you're going to learn about in linear algebra. All right. So this really just kind of details what I was talking about above. You know, a lot of hand waving, but this formally addresses it. And this gives you a formula that allows you to figure out the component form of the vectors. All right. So how did I figure out the vector PQ up there? I found the difference between the two x values and the difference between the two y values, except I did it in a more geometric way. All right. So this is a little shortcut approach for doing stuff like that. So if you want to apply this in this situation, express vector v with initial point. This would be x sub I and y sub I. And this would be the terminal point x sub t and y sub t. Then vector v is going to be equal to the differences. So 1 minus negative 2, and then 2 minus also negative 2. So 3, 4. All right. If somebody's looking for typo opportunities, here's one for you. I have no idea why I have so much space after the definition. Vectors are said to be equivalent vectors if they have the same magnitude and direction. That is a fact. There is no need for any of that space below it. So I gave you space for that, but on that last problem where you could have used a little bit of more space, I did not. So I don't know what's wrong with me sometimes. But yeah, if somebody wants to submit that, just again, just on remind, just send me a message, page 18, under definition, remove the space. And I'll know what that means. Vector operations, adding and subtracting, very easy. You're just adding corresponding parts. Scalar multiplication, very easy also. You're just distributing the scalar multiple through the vector. All right, it's when you get into vector multiplication that things start getting a little crazy because there's a couple of different types. All right, there's something called the dot product and there's something called the cross product. Definitely different subjects for a different day, but it's coming. And it's pretty procedural, but it can be a little mind-bending, somewhat mind-bending. All right, so I have vector m is equal to 5 comma negative 7, and n is 0, 4, and p is negative 1, 3. We want to complete the following operations. That doesn't feel right. Compute the following. Forget the operations. That is just that the language is weird. Honestly, I think I copy pasted that one from OpenStax. I don't like that. It's just awkward. Compute. Hello.
Yeah, that definitely sounds like something in a textbook would be said. I think something you said.
Yeah. At the end of this course, you could be like, I learned a little bit of Calc 3, but I really, really helped Professor Can fix his note packet. That's really why we're all here in the end. All right, so m, 5, negative 7, plus negative 1, 3. So very simple. Add the corresponding parts. No need to memorize a rule. I try not to overuse the term common sense, but this might fall into that category. All right. Like if I didn't give you any instruction and I just gave you these values and I told you to add m and p, this is probably what you're coming up with. All right. So intuitively, you already knew how to do this. Maybe even number 2. Except I wouldn't even show the step of actually writing 2 as a coefficient of m. I would jump right to doubling m. All right, so I got my m over here, 5, -7. I'm going to double that, so 10, -14. Then I got my n over here. I'm going to triple that, so plus 0, 12. And then the last one, I'm still going to use addition. I'm going to negate it just to make the addition ever so slightly easier. So 1, -3. I don't have to worry about mixing up operations. So 11. -14 plus 12 is -2. -2 plus -3 is -5.
Why did you bring the negative?
Oh, because we're subtracting. So it's a constant multiple of -1. So I negated this.
Oh, okay.
Yeah, I just
I
did
missed
that.
the.
Shit.
-14 plus 12 is 2.
Negative. -14 plus 12 is -2. Right. There is a way to do this on the calculator. It's just more trouble than it's worth. So I think at this point, because you know how much I like the calculator, that when I tell you that something is not going to be good for you to do on the calculator, hopefully at this point you believe me, and we could just kind of skip that part of it. But GeoGebra is really great for this stuff. All right, so that's where things get exciting. So the graphical way of finding the sum of 2 vectors. This is something that I like to put on the test. It's another kind of, well, middle of the road kind of gimme question. It's not the 30-second one, but it's kind of like a step above that. Very doable, but people often fall into the trap of just not doing it the way that you're asked to do it. It says graphically find u plus v. All right, well, I can do it using arithmetic.
Oh, are you supposed to connect the two?
Yeah.
That.
I mean, looking at this, I say 6-4 and call it a day, but it says graphically do it. All right, so there's 2 ways to handle it. I like using the parallelogram approach. That's just my personal preference. There's a tail to tip approach that also works, but I don't like that one, so I'm not going to go over it that way. All right, that's just the way it is for me. So what you're going to do is, and I think an index card or the side of a sheet of paper really gets the job done. All you're going to do is take the side of a sheet of paper. Oh, geez, this is perfect. Oh, wow, I couldn't have planned that either. I did not plan this. All right, exactly 11 inches long. All right, so what you're going to do, if the line segment were longer than the side of your sheet of paper, you just mark the beginning and end, and then just translate the whole segment over, and then plot a point, and draw a line segment. All right. So it's not going to help me to draw it here. I just need to kind of get a landmark. Below the O's and kind of in line with the top. Okay, I'll figure it. So you're really kind of eyeballing it because I'm not looking for any kind of great accuracy, because you've seen my drawings. They're not good. And I'm generally, there are exceptions, but I'm generally a practice what you preach kind of person. So, like, I can barely function in the art world, so I'm not going to ask you to make anything too stunningly gorgeous. All right. So, plot a point that you think would represent what that end of the line segment would look like, and then use your line draw tool to draw a line segment, and then you'll be in pretty good shape. aka a ruler or something along those lines. Side of a finger works pretty well in the absence of a ruler. Side of a pen, I've done that. The index card that you use to mark things off, you could do that too. The slope looks a little off, so I'm going to redo it, but that's just a me thing. Yeah, maybe like over here, I think. Yeah, it looks a little nicer. All right. Then what you would do is the same thing with vector v. Translate that up and connect it. But once you've already translated one of them, you just connect the dots, and you'll already have the translation of the other one. All right. So that's this bad boy. That's not that bad boy. I think freehand is really. Ooh, that's disgusting. All right, so then once you have your parallelogram, draw a line segment going from the origin to the outermost point. That represents vector u plus v. So we label that up. That point should correspond with the actual sum of the two vectors.
Wasn't this just twice as much work as the tail though?
Wasn't it twice as much work as the tail to tip?
Yeah.
Maybe, yeah.
Isn't the tip and tail like just dragging the bottom one up to the top? Or the top, or the
Right.
Yeah.
But what's going to happen, and so we got to do this in 3D. So this ends up being a little bit nicer in that regard. So yeah, once you get that Z component in there, things start getting a little crazy. So I've done it both ways, and I just kind of settled on this way as the way I like more. But I mean, if you know the other way and you want to do it that way, that's perfectly fine in 2D. I would ask you to keep an open mind once we go to 3D. Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so it's not even anywhere near. Oh, actually, no, that's perfect because I didn't include the numbers on this, but these are half units, right?
Yeah.
Yeah, because this would be 4, 1, but it's 8 tick marks. So that actually works. And then 1, 2, 3, 4. Well, that's a little more. Oh no, these go by ones. So that's actually it's actually correct. All right. So let me label up the horizontal axis. I'm always surprised when my graphs end up working out nicely because it's just not a thing that typically happens. All right, and so we get u plus v is equal to 6, 4. All right, and again, you knew that from just doing the sum, but this helps you develop a visual. Now, I gotta tell you that people have done this in the past, and it really, I mean, it aggravates me, but like not to the point where I'll lose any sleep over it because I just take off full credit and then I get over it very quickly. What people will do is, oh, you want graphically, huh? 2 plus 4 is 6. 3 plus 1 is 4. They plot 6, 4, and they draw a line segment to it, and they say, well, there's your graph. That's not this. All right. Yeah, I mean that's I guess what people do when they panic and they're like, oh, I meant to study this, but I didn't, and now it's here on the test, and he's gonna know that I didn't study it. I got an idea. This is gonna be on the test. Study it. I am going to put this on the test. Maybe even this exact question. I don't know, something very similar to it. All right. One semester I put a 3D graph on there, and I would have had everybody's tests graded within a 24-hour period like I like to do, but because of that one freaking question, it took me like almost a week. Because 3D graphs, like even a crappy graph could be correct, and it's just hard to evaluate what's right and what isn't. So, yeah, on a piece of paper, yeah, it's a nightmare for me. So just for my own sanity, I'm like, you know what, I'm gonna put this concept on there, and I don't want to be spending the rest of my life grading it, so you're getting a 2D graph. You're not getting it. So maybe it's not 2 and 3, 2, 3, and 4, 1. Negate, I don't know, something like that, but maybe a little twist on it, maybe a scalar multiple involved, but it's going to be something very much along these lines. And so that, I mean, you can't get any better than that as long as you actually do your part and study it. This last one here, I'm going to put a star on it, but I'll just give you kind of a quick sense. It's asking you to use these actual line segment lengths. You don't have to use them in the position that they're in, but what you do have to do is take note of the length of vector v and the length of vector w and come up with these different relationships. 3w should be pretty easy, just triple this length. All right, and you can do it anywhere. It's probably separate paper, I would think. V plus w, you're going to use the similar idea to this. Just when you plot v and w with the appropriate lengths, just pin them at the same endpoint. All right, it doesn't necessarily have to be at the origin. It could be in space, but pin them at the same endpoint. And then create your parallelogram and go from there. This one is a little twisty, but I want to see if you can figure it out first before I give it away. All right, so that's where we're going to leave it tonight. And next class, we'll do a little bit more with the derivatives of polars. I'll try to budget more time to do another area question with you, and then we'll continue on with this stuff.